All right, welcome everyone to this June edition of the Community for F#. Today we have a double header for you. We'll be starting with Anton Tayanovskyy talking about Reactive DOM, and then later tonight the Seattle F# user group will be hosting a talk on Dataflow networks. So there are actually going to be a lot of probably crossovers between these two talks, as both are going to be talking a little bit about data flows in various scenarios. Before we get to Anton, I want to just briefly mention some of what the Community for F# has been doing. We have updated our website, which I think we showed before, but we also have a few additional things that have happened recently. Reed Copsey has added pages for upcoming F# events and F# user groups, so you can get a good overview of what events are coming up, where they're occurring, and you'll see very quickly that there are events all over the world for F#. So please find a local event, support your local user groups, support your local conferences, and check that out. We've also started a LinkedIn page where we're posting jobs. I don't have a link for that at the moment, but if you are looking for a job that does F#, look for the Community for F# LinkedIn page and the jobs page there. All right, and now I'd like to introduce Anton Tayanovskyy. He is an avid F# hacker working with IntelliFactory to bring the benefits of F# code to HTML5 and JavaScript land via WebSharper's F# to JavaScript compiler. Anton enjoys solving problems with functional programming, composable libraries, and types. He delights in digging up ideas from old and recent computer science research. And you can find more about him at toivo.github.io. That's T0YV0.github.io. And with that, I'll hand it over to Anton. Thank you very much, Anton, for joining us today.
Hi, everyone. It's a pleasure to be here. I hope you can hear me okay. Thanks, Ryan, for having this event. What I would like to talk about today is present a library that we are developing as an experiment at IntelliFactory that helps you construct user interfaces, especially ones that are based on HTML5 and the document object model, using F# in a way that's hopefully a little better or a little clearer than what's been available before and not what you might imagine. We don't have a good name for it yet, so we've been calling it WebSharper.ui.next, and in the group chat there is a little link to the website with samples, which I will be also using to screen share and hack on during this talk. So please feel free to have a look there, and some of us prefer to just browse through everything without waiting for me to explain it. Those of you can go to the website directly.
Hey, Anton, real quick, if you don't mind selecting yourself in the bottom right of the Hangout, just so that your video appears. I'm still seeing the C4F# website at the moment.
Actually, I did that.
Oh, okay.
On your end, maybe something's different?
Yeah, let me unshare and see if that works. Okay. Please continue. Sorry about that interruption.
Oh, excellent. So I hope everyone can see me now. Yeah. All right. So UI next. What is it? What can it do? Let's go straight to that link. Oh dear. Oh dear. Here we go. And let me actually start screen sharing here, so you can easily follow what I'm doing. Full screen. Oh, not a good idea. Okay, Ryan, can you follow now the screen? I'm on GitHub.
Yes, I see it.
Excellent. So here's a very, very simple example of what we can do here. Here is a little input box that I just selected. And whenever we type into it, it gets reflected in a label below the input box. Simplest possible thing that illustrates the concepts that we are aiming for. Let's check the source here. Here is the. So how could you model this? Well, we all know that if you worked with the browsers, and there's this document object model, you construct graphs of mutable things. You can subscribe to events, you can handle them, and so on, so on, so on. But what we are trying to accomplish with this project is to kind of simplify that a little bit. So that, for example, when all you're doing is synchronizing some state between two different places in the application, you don't need to worry about directly handling the update events. And I will go into a little bit more into why you would want to actually abstract over this. So in this example, here, I hope you can see my mouse, is where everything happens. Here's the label, and here's the input field. And it's composed in an F-sharpish DSL, or that kind of thing, to form what will effectively be a time-varying DOM tree, document object tree. First, we create a model. A model is just a simple var, as this library calls it. It's a time-varying structure. So RV text is a var string. If I look it up in Visual Studio, we can enjoy type checking. So there's a type var, and RV text is of type var string. I hope you can see that. And then we tie it to an input field by creating an input box here with that var. And then we also tie it to a label. After that, we compose it all together, and that is all we have to do. You might notice that we actually did not have to handle any events or clicks or things like that. Well, so why this, and why what's different from before? Well, I think big motivation is people have been asking, so how do you construct front-end things like JavaScript MVC things with WebSharper? And our answers before have been centered around basically doing what these JavaScript things are doing, which is typically subscribing to events and handling that in a standard fashion. But it didn't compose very well, so here we are trying to improve on that. We also realized you can't really, to take full advantage of HTML5, you can't very easily say that you have a closed vocabulary of things, because the vocabulary keeps changing under you. The HTML5 keeps evolving. There are new things coming out. So here we are not trying to constrain, for example, the div element. You could basically have any kind of element here that you want, because we don't yet have a closed vocabulary of element types. Another thing that we learned from before is that since we are constructing this before we had different types for nodes and node lists, and that goes to bite you. For example, here I can refactor. Name to a fragment of the tree and put it back. One element, but it was a collection of elements. For example, a div followed by a text node. Before that, in WebSharper, we had different types for lists of elements and for a single element. So you would get type error, and then you would try to do something like use F# notation to make things work. Unfortunately, that's a little bit inhibits your style, and sometimes you have to do this very annoying refactoring which make you think about whether it's a list of nodes or a single node. We realized that since we are never pattern matching on this HTML fragments we create, we only create them, then an excellent idea is to have a modoid for the interface, that basically it doesn't matter. We can always concat a list of these things into a single thing, and it will just work. And actually, if you go back here, here's a good overview of this combinators with an FSI file, which I find to be sometimes the clearest to explain what's going on. So the doc type runs a time-varying node, or a list of them, such as an element node or a text node or a collection of them, and it can change over time. The monoid that I talked about by these combinators here. There's an empty doc, there's an append, and there's a concat, which is generalization for many appends. It's like a fold. You can create elements by giving a name and attributes, which are also time varying, and sequence of constituent nodes. You can create text nodes that are static, and it's just a special case of dynamic text nodes that can also vary with time. Now I've been a little bit hand-waving about this vary with time, but let's look into that a little more. Oops, I shouldn't go there. OK, so when I say time varying, what do I actually mean? As we were working on the library, we realized that actually time varying DOM trees are very fine, but trees vary. And we want to be able to express time varying structures regardless of what they are. So generic over a T type. We basically talk about Dataflow network to be able to and perhaps a picture with here, and I'm going to use this interesting tool called Whiteboard to draw some pictures about it. Let's see if I can escape screen share. Oh, hello. So, what are we after with Dataflow? Basically, the simple idea is that you have several variables Oops, I guess I have to learn to writing from right to left. That's a strange effect of this screen share, but anyway. You have a few variables that are basically like ref cells in F#. And that's your model. That's the current state of what your user interface is about. And then from that model that you can change using callbacks as before, as you would normally do in the UI, you construct several views. For example, you can map a function here. I guess it should stick to pictures without writing because it just... So here's one function. You can map another function. You construct two views. You can join them. So this kind of structures will allow you to do what? The data will flow to this according to this tree. And we expect that, in fact, you will try not to create cycles there. So we don't even discuss what happens if you create cycles. So you can imagine there's a static kind of tree that you form. And then whenever there is a change to one or many of these variables, what happens automatically for you, provided by the framework we're building, is that the dependent nodes get recomputed. And if these dependent nodes have been inserted in some way into a DOM tree, then this DOM tree effectively gets presented to the user and everything goes on. So the advantage of using this is that you kind of decouple your model, which captures the current state of the interaction with the user, from different presentations and even independent presentations of that same model. And it actually maps very easily onto types in F#. And I will show you a few combinators now that relate to this. But first, I would also want to mention that it's a little hard to depict this as on the whiteboard, but the data flow we are actually talking about is dynamic. So sometimes it's not just a simple static combination of arrows and nodes, as I showed. Sometimes what happens is parts of this data flow start one way, and during the execution of your application, during the time when it interacts with the user, the shape of the graph changes. So it was this way, and then new data flowed in, and this node was dropped. And then this whole thing was dropped. And then another thing was added. many things can happen. And in fact, it turns out that to express it in F#, we just have a handful of combinators that enable everything. And you do not need to worry about these things too much, or use imperative do this, do that, subscribe, unsubscribe, or change the graph, because it kind of falls out naturally. So let's go back to our F# code and look at some combinators. Screen share. All right. So this little file here that you can also access online at this GitHub URL lists the main combinators we have for generic time-varying structures. This is a var type, var_t, is a time-varying variable. It's like these top nodes that I drew. And view_t is a type for views that you construct on top of the variables. So the variables, what you can do with them is just like with refsolve, you can create, you can get a value, you can set a value. Update is just a helper function to get and set. And what do you do with views? There are constant views that represent something that actually never changes, but also is a special case of something that can change over time. You can construct a view from a single var, from var. You can map lift functions to become functions on views. This is how you construct very basic transforms in this graph, like one-to-one. There is a map_to function that pairs up views, and based on this, you can do applicative-like combinators if you want, which we'll see examples in code. And there's this little thing called join, which enables dynamic composition. So actually, the shape of the graph can change over time, and this is how you accomplish it. Together with map and join, we can define bind, and we can define a computation expression builder if that's something you like. Basically, the rest for now is not important here. Those are the things I wanted to touch on. So let's look at some other example where it goes than what I showed you. We go to examples here. Let's look at this example, which I basically copied part of the Angular.js tutorial here to see how could we do it with F#. There's a list of phones. You can sort them in different ways. And you can search. And when you change the search box, the list of phones automatically changes depending on what you typed. So that's pretty, I guess, old news for anyone who seriously works with user interfaces. What's interesting is how do we express it using the data flow, using vars and views. Let's go to the source. OK, so first of all, in F#land, as much as possible, we try to just use data types and simple functions, right? So we define a phone. We define ordering values. We have some helper functions, how to map them to text. We have a comparison function that actually provides meaning to the order type, so it can compare two phones. We have a search function that performs the search by matching your query against the phone. And let's jump to Visual Studio here, so it can also show you types.
Anton, real fast, would it be possible to increase the font size in Visual Studio?
Definitely. Is there a shorthand to do that? I would love to do that.
There is a plugin for Visual Studio called Presentation. I think it's like it'd be too long to probably install that at this point. But the percentage at the bottom, on the bottom left, has a percent at on the bottom left of the text document field, and you could just be like 150. That might be a little large. That looks great.
Excellent. Yeah, that's a very good thing. I hope it's a little better now. Yeah. So just here to type it out, you can look at types that are inferred by F# to this. So compare takes an order, two phones, and returns an int depending on how they compare. Match query takes a query string, a phone, and returns if it matches or not, a boolean. A bunch of utility functions. So let's define the model. First of all, we have a database of phones, like a list of phones that we are trying to display. We create one var create. All phones, we create a query var to hold the current query that the user inserts. We create a var for the current ordering. So together, these variables, one of them I think is actually constant, so we can refactor it a little later and remove it. But anyway, they define our model that we try to present to the user interact with. So how do we do that? We create a view, first of all. Visible phones will be a subset of all phones that is filtered by the search string, and then it's sorted by a current query. So first we create views from var takes a var to a view, and there's a different way to write it right now. It's like that, a little simple. So we take the order and we put them up to compare two views into one view, and the value of that paired up view is a function of the values of composite views. We just take all fonts, we filter them to match the query, and then we sort to compare. So the visible fonts then is a time-varying list that depends on the model of our widget here. And all we need to do now is to map it to actual UI, map it to the document object model so we can show it to the user. Here's how we show a single phone. You can recognize this as like a little HTML-ish thing. There's a list element and a span element and a paragraph element. So this takes a phone to the doc, which doc is a document time-varying node list or a node in HTML that you can later embed into other things like that. To show the phones, we take a phone list and we produce a doc. It's easy to construct here. And with some presentation, we create first we create here a form input box tied to our variable query, so that will actually work both ways. So if your application sets this variable, then input box will reflect it. If the user interacts with the input box, then the variable will be set and the model will proceed and all views will recompute that are based on it. So as you see, we just accomplished this without actually using callbacks in this case. A select box, another helper attribute we have. To produce this, all right. So select box needs it's parameterized over some arbitrary type. We need to show that we can create a label for every value of the type. So there's a t2string function, list of options, and also a variable that it ties both ways to. So there's a variable, there's a list of variants, and that's how to show labels. It takes care of that, and it's positioned inside the div as we want to lay it out somehow. And finally here we oh, the communication is a little outdated, but never mind. Finally, we have this funny function doc embed view that takes a time-varying document and produces a document. So basically, the document type, it's kind of simple type that contains everything. It contains nodes, nodes list, and it also contains this kind of strange nodes that change over time. Here's all we do. We take a view of a phone list, which is a visible phones. We map it with a show phones function that produces a doc, and if we have this, we have a type for that intermediate expression here. It will be easier. We get a view of type doc, so it's a time-varying document, and then we just embed it into an actual document. And we're done. And the rest is just boilerplate with the database of phones and how to run it. How to run it, once we are done with creating our final time-varying document, we just take an DOM element or maybe an ID of this element, we inject this time-varying structure, and it proceeds to show it to the user. So far so good. This was a bigger example. Let's go back again to see how it looked. Yeah, here's how it looked. So all interactivity is kind of, sort of, kind of for free with this view environment. Now, there is a little bit of a problem with this approach that we had to think about, and we tried a few wrong approaches before I think we came to the right approach. The problem is that we are talking here about a dynamic fragment, and we are talking about sharing DOM nodes. You think that DOM nodes are immutable, it would be a big mistake. Not only they are immutable, they also often contain widgets that have some kind of internal state, and we don't even know what it is. So if you try to recreate and reattach DOM nodes on every update, you get into trouble with certain kind of DOM nodes. Let's illustrate this. Let's say change the code here where we show the phone, because something that right now has a signature from a phone to a document, and it gets called every time with the new phone. So let's change it a little bit, and let's inject a simple element like an input box here. And let's see what happens. All right, so we just injected input box. They appear for every phone, right? OK, so fine. How about the user interacts with these input boxes a little bit? So I put some things into them, and then I change something here. I change the ordering, for example. What just happened? All my interactions are gone. Try it again. As you see, this is kind of worrying. This is kind of broken. Something that I expected to just work out of the box doesn't work. So how to deal with this? Well, if you look at the code again, what actually happens, to show a list of phones, which was time varying, we just map this function, which means that it creates a new document of a given structure every time anything changes. So when we embed things, view map show phones on visible phones, whenever the visible phone list changes, we call the show phones function again and again and again, and we do not do any sharing here. So the DOM nodes generated are new, and they're different, and you could observe that. Now, you might look at some JavaScript frameworks that try to tell you that they try to deal with this somehow. For example, they can do this virtual DOM that they'll try to deal with it by recovering sharing automatically for you, in this case. We experimented with that, and we found that it seems like it's a problem that in general is not even possible, because sometimes the user wants to generate new nodes, and sometimes you don't want to generate new nodes. So it's basically should be a problem that you kind of expose to the programmer and let them deal it either way they want. So, and when we thought about it a little more, we found out that it actually is not necessarily, strictly speaking, a DOM problem. It's a problem with how, at the level of the var and view layer itself. And it probably deserves to have combinators in that layer. And we thought about how such combinators might look like. And basically what happens is that you can design combinators in addition to the plain ones. You don't have to muck with the plain ones like map. You can define combinators with a little more structure that would allow you to construct Dataflow networks that would do more sharing. So let me show you quickly how the signature looks like, and then I'll draw you on the whiteboard to explain what it might be doing. So the signature here. here's one of such combinators that we designed. So what we are talking about, it's like a map, except now we are specializing and we are dealing with views of sequences. So we want to map a view of an, let me make the font size larger as well. We want to map a view of a sequence of A to a view of a sequence of B. And we could accomplish that by a simple map by lifting, for example, sequence map and then view map and composing them and obtaining a combinator. But as written, what that would do, it would call this projection function that we supply, the A to B, every single time the inner view changes. And that's a little bit suboptimal. What we are going after here is saying, OK, suppose we have equality on A. It means that we can compare two A values for equality. We can exploit that to kind of memoize this function, sort of. Well, we can actually also have a combinator that does memoizing in general, but that is a little problematic in itself. So let me try to switch to whiteboard and try to explain exactly what happens here. All right? OK, so at one point in time, you had an empty list. Then you had 3 elements. Then you had 2 elements. Then you had 3 again, or something like that. There's just a trace of the evolution of a view of something that has a type view of a sequence of T. And if you have identity on these elements, we can actually track that these things are, are the same. So for example, in this transition, what happened was the 3rd node was removed and the 2 were kept. And for example, here, this node was kept and the other were removed. You could have collections that explicitly make this information available, and that would be one way to use it. Or you could have an approach that tries to recover what happened just by using equality. So if you're treating your collections as a bag, for example, this is why we are using bag in the word. It means that we don't really care about order, we just care about equality. So you have 2 sequences from this time period, this snapshot and that snapshot. And you have equality on the elements. You can actually compare, using this equality, which elements are the same as before, and which elements were added, and which are removed. And using this information, which is like a kind of a diff on bags, using this information, you can perform better mapping. So if we had this one collection, and let me erase this, and we have a mapping function that takes circles to triangles, for example, right? Something like that. So on step 1, we had 2 circles, and on step 2, we had 3 circles. And we want to obtain a new sequence that mapped these 2 triangles. I hope you can see that. My triangles are not very triangular, but hopefully that doesn't matter. So if we have identity and we perform in this diff on every step, then what we can actually do is that first we observe 2 new circles we didn't see before. So we create new triangles for them using the function that the user provided. On the next step, we observe that these things were available before, and using the diff information, we reuse the triangles from the previous step. But there is one new circle, so OK, we use the function again to construct it. You can see how this works. Now, how is this different from memoization, you might ask? Because if you just use generic memoization on a function using equality on the circles, then it would only create, it would reuse triangles throughout the whole execution. The difference is that we don't want a memory leak here necessarily. I mean, it can be, the strategy should be, again, both strategies should be available to the programmer, because sometimes you do want memoization, sometimes you don't. The memory leak I'm talking about is that suppose this user interface you developed is running forever, non-stop. The users keep interacting with it, the view keeps changing, and it goes through many, many transitions. Now, if you had the memoization function there, it would imply some kind of a table. So this table grows and grows and grows, and so if the users keep exploring new kinds of circles using this identity, which is not bounded in any way, then your memoization table grows indefinitely. However, a very common in practice case is that when you only want to memorize over one transition. So, for example, if using complete memoization, the table would live indefinitely. Here, what we are suggesting is that it only lives for a delta 1 in the step. So it only lives for one step. So if you introduce a new node in one step, and then later you remove it, and then you reintroduce it, the memoization table will not be able to figure out that it has seen it before. It will reconstruct it. But that is fine. And actually, for most user applications, this is enough. And what it gives you is a guarantee that your table size is bounded by the largest sequence that's going to go through that reactive view, which is a nice property to have. And actually, the idea for this came from analyzing how, maybe you know this data-driven documents, D3.js, which is an excellent library with a very strange interface. The idea for doing this came from analyzing what they're doing with creating projections and elements. And in D3.js vocabulary, this is called enter and exit selections. So whenever there's typically a mapping from some kind of data nodes to visual nodes, and it's a one-to-one mapping. And what they're tracking is they're tracking at every update which elements have been kept from before, which were added and which were removed. So what we did here is just a generalization of this idea to an arbitrary T that has equality. And how we use it with document object model, let me show you some more API here. Back to screen sharing. Hold on. OK, so that was on general level, but we can also have a specialized combinator for the same thing in the document type. Here it is, embed bag. So it's a specialization of that combinator to documents. So once you have a render function that takes a T to a document, and we have a view of a sequence of T, and we have equality on that T so that we can actually distinguish if things are the same or not. We construct the document. And why is it better than just using a map as before is that it has a limited memoization table, so it doesn't call this function too often. And now let's look at an example that does it and see how it's different from what we've done. So going back, yeah. OK, here is a todo list example. It's basically a vanilla todo application that you can add entries, you can mark them down, you can remove them. And this one actually uses embed view. So if you look at the source code here, forgive me, I'm going to make it smaller for a second. And let's perform the same experiment, right? Let's look up how every item is rendered, and let's add an input box there and see what happens. Because here, when we render a todo list, we are actually using this embed bag variant of combinators instead of just plain mapping. So let's look up render item. Let me make this bigger again. Render item takes a to-do item and produces a document, and let's just insert something here, like an input box that's going to be stateful. Oops, I missed. Yeah, there we go. There we go. As you see, every todo item now has this strange input box. But if I modify it, and then I keep modifying the list by adding new items, then the state of this thing is preserved because we are taking advantage of the cache. We're not generating new nodes, and they retain their internal state, such as focus or whatever value they have. Other than that, it works as expected. So that was that concern and how we handle this. Now, maybe it might be worth it to go through the through the source code of this to-do list. Basically, this illustrates that variables can. Oh, let me just jump right to Visual Studio here, actually. Right. So a todo item has a variable done flag. It has some kind of unique key that identifies it, and a text. And then we have multiple of those things, and I'll explain this in a moment, but it doesn't matter for now. What matters here, perhaps, is that you see that you can use static variables. You can use variables inside the model. It depends on what you're trying to accomplish. That's the flexibility that provided by the var type, I think, is pretty great. Because here, we know that the only thing that varies is the todo flag. When we render the item, we say, OK, every item maps to a table, and whatever the input box we inserted, let's remove that. And here, we actually take the done flag, and depending on its value, is done, whether it's true or false, we render it differently. We render using a del element, or we render using a plain text node. And then we embed this. What happened here is that you see that there's going to be change propagation in the Dataflow graph. So when an item will be rendered and its todo var will change, this TR and TD elements will not be redone, because what you're actually tying to the model is only a fragment. So that is taken care automatically. So that's that they don't have model all in one place, whenever it makes sense to have variables inside your items. Other than that, we have some buttons here. And what we're actually suggesting for now in this framework is keep using callbacks. So here's a button. And what it does, it sets the current todo's done flag to true. That's what it does. It could have updated it instead, for example. Oh, I missed my order, but data that is in not function, it will become flip then. It will be like set or unset. Try to say, OK, this example needs some kind of custom collection, because we are talking about a list of items or something like that. And when we thought about it, we realized that no, we can use an existing mutable structure such as resize array, also known as a system collections generic.list. What we're rather interested in is we are saying that we would like to track modifications to this resize array wholesale. So basically, we want to be notified whenever it changes, and we can observe these changes. So we wrote a little bit of helper code, which is basically like 20 lines, called this model type, that basically allows you to guard a mutable collection by a single variable. So when we create our view model here, we take the actual view model is this particular resize array. We just lift it to the strange model type, and we give a projection function that takes a snapshot of that array in time, as the snapshot is of type todo item sequence. So you see what happens here. The resize array can change over time, but we can observe it at specific snapshots as a sequence of items that's not going to change. And this is all encapsulated in this like view model type here. So what the model combinators give us, we can have an update function that will allow us to just modify this resize array mutable thing, but modification is tracked so that actually other parts of the code can observe it. How do they observe it? To observe it, we have model view function that takes the items, right? And it observes the changes in that mutable collection. So it seems like maybe I'm not explaining it too clearly, but what I would like it to retain is that The framework actually doesn't need to reinvent every single possible mutable collection and make it reactive so that you can embed it in the reactive data flow graphs. What suffices very often is to just guard access to that collection through one reactive variable that you can observe changes to it, and you can use any kind of collection here. You can use resize array, you can use dictionary, hash set, whatever makes sense to the particular application. All right? Perhaps at this point, if you haven't done already, I encourage you to look at the rest of the examples. Let me quickly.
Now is probably a good time if you have any questions and you're viewing or watching. The Q&A should be showing up in the YouTube feed or on the website, the event website, that is. So please submit your questions, and we can read them and answer them on here. If I may, Anton, I have a question for you.
Oh, please, yes, of course.
So one thing, when you were talking about the reactive DOM, one thing that stood out to me is it seems like a lot of the virtual DOM implementations think about modeling more, I guess maybe a data model, and then how that maps into a static snapshot of DOM nodes. Whereas this seems like you're really more modeling the actual DOM itself as a first-class citizen, and then binding it in using the model type. Is that sort of accurate in terms of the impression I got?
I'm not sure what the fine distinction would be here. We definitely are modeling something that is hopefully close to your intuition of what DOM is, which is a tree. So basically the intuition is like, I see some HTML code, and now I want to make it dynamic. So I construct something, and it's mostly static, but there are some parts that will vary over time. That's the intuition. That's what we're trying to help you write. The actual implementation is not directly mapping to DOM nodes. In fact, it's batching DOM updates, it's doing some work to minimize calls to the DOM API. It just tries to do most of the things that the virtual DOM things do, except we are not making promises that are impossible to promise. Like, for example, the virtual DOM things say that if you have, they automatically perform a diff for you, and it's always right. And I think that it's just not going to work. So there's examples where you cannot perform an automatic diff, and we don't try to do it except as a strict optimization where we know it's going to work. Instead, we're trying to find combinators that will let you as a programmer express in what way the identity of your widgets are gonna be used. Does that answer it or not really?
That is a good job of answering it for me. Thank you. Another question that I have, and I'm sure a lot of other people would be thinking about too, is what does this look like in terms of performance? There's been a lot of performance measurements of different frameworks one against the other. Is this at a state where it's optimized, where it would be comparable, or is this? Have you even done any performance measurements to see what the current performance is and how it stacks up against other implementations or frameworks?
I think at this stage it would be premature optimization. We are trying to figure out what are the combinators we're after, and there is a very important possibility for performance, and I think it might be realized right now, but we don't have yet benchmarks. The possibility is that most frameworks, including like RX, GS, and all sorts of things that provide event stream combinators, which we don't provide, they make a mistake of over-specifying the semantics. So when, for example, you map from one event stream to another event stream, you're saying that on every event in the input event stream, we want to call this function, and then this happens. For many, many problems in user interface programming, this is an over-specification. What we really want to say is, here's a time-varying value that depends on another time-varying value, and I want this relationship to hold in time.
That was odd. Sorry about that, everyone. Anton, I think Google had a blip. And we lost the feed for a moment.
Yeah.
Okay, please continue.
So what I'm talking about here is when we have two views in our framework, and they are related by a map function, like you mapped a function over a view. The framework is free not to perform a computation on every update. For example, there is this little map async combinator that we are exploring that actually maps an asynchronous function. And of course, the asynchronous function can get stuck doing network I/O or whatever. and then the user doesn't need to get stuck together with it. The user can continue making new requests to the framework. So what our library will do, it will stop trying to deal with the old stuff, and it will actually start dealing with the new stuff. And it's free to do it under the semantics. So there's a lot of potential for optimization here that I think other frameworks miss. Unfortunately, I think you're muted, Ryan. I cannot really hear you.
Yep, and my screen keeps freezing.
I'm sorry.
Yeah, that makes a lot of sense. Thank you for explaining that.
If you're interested in frameworks that we actually liked from looking at different frameworks, and I suggest you look at Elm language, which is pretty cool, but it has to invent a new language and a new type system to actually prohibit some pretty nasty dynamic things. But it's a nice language, but it's just not an option for us in F#. We like React, but not the Facebook React, but the OCaml React library that implements functional reactive programming, although we decided not really to go for that at this point. But we might revisit this decision later. And of course, if you haven't checked it yet, check Concurrent Programming in ML, a book by John Redby, and check that if you have access to a library. A great book that told me everything you would ever want to know about user interfaces was a 1984 book by Tony Hoare, Communicating Sequential Processes. That's just an excellent read that sets a framework for thinking about things. Those are the things we like, but our library is very limited in scope, so we're trying to do only a part of that.
Cool. I'll try to add these links as, I guess, show notes in the Hangout page.
Excellent.
Unless, Anton, you beat me to it. Either way.
Oh, excellent. It would be good to add them.
All right. I don't see any other questions popping up. Is there anything else you want to share or show? I think one thing that we've talked about in the past is that in terms of other existing pieces of WebSharper, like piglets and formlets and whatnot, one of the things that I think we discussed was whether or not this would actually be able to be used in conjunction with those. Did you want to explain a little bit about that? Like, does this mean that WebSharper has to change completely, or is there a way to merge the different existing programming models?
Well, I think there's a lot of potential for merging them, but I think some things will have to change completely because they're just not very helpful. So, for example, the HTML combinators that do not use the monoidal interface that you're using now, I think also will have to go because it's too much of a burden to maintain. We'll maintain backwards compatibility for like a year or so, but then we'll have to. I think this works just so much better. About piglets and formats, I think those suffer a little bit from what you might call a Haskell syndrome. Like it works very well if your specific problem domain exactly maps what it was designed for. As soon as you're going to the left or to the right a little bit, you find that difficulty to express yourself, which to me means that there should be some kind of another layer that that UI Next is trying to put under them. That is a little more general, so it's a little worse for those specific things. So if you want to design a form with validation and whatever, then formlets or piglets would give you a lot more, and it will accomplish the job faster. However, if your application differs from that model in some way, then the more general combinators would be very handy. So I think that we felt the need for this ourselves. We are developing it as an experiment, and it seems like it's so far at least helpful. As far as formlets and piglets go, they will probably be able to use it and build on top.
Excellent. All right, and I think we're going to try and have Loic on in the future to talk about CloudSharper. Did you want to give a kind of a preview of what that might be about, or just a snippet about the tooling that IntelliFactory is building there?
Actually, I wasn't preparing for this, but sure. I mean, if Loic is here, we could switch. Give him. I'm not sure if he's listening and he will sign up, I think. But yeah, CloudSharper is basically IntelliFactory project to create another development environment for F# that works cross-platform and will eventually work in the browser like Gmail. So you can log in and have your code and edit it with code completion and stuff like that. And then we're using WebSharper, F# to JavaScript compiler platform to build CloudSharper itself, and we're also integrating CloudSharper with WebSharper, so it's installed by default, and you can use it to construct web applications. It's a good project. I think once it succeeds, it's going to be pretty nice. I also must say we learned a lot while trying to make this. There's some new areas that we didn't know much about. And to some extent, what I think we learned about user interfaces is also was the result of working on that project. So Loic will probably be presenting the current status of it, the current state of what you can do, and it should by now, the cloud mode is not yet available, but it works on Mac and Windows by now, so, and it's kind of nice, like it runs in the browser and stuff like that.
Well, fantastic. Well, thank you again, Anton, for joining us today.
Thank you, Ryan.
We will have this recording up fairly shortly, so if you know anyone who missed it and wanted to see it, or if you want to watch it again, look for it on YouTube, and we'll send out the link on Twitter. That's at C4F#, letter C, number 4, F#. And again, thanks, Anton. If you want to follow him and see what he's working on, you can follow him at T0YV0 on Twitter as well. All right. Thanks a lot. Have a wonderful day.
You too. Thank you.
And don't forget that tonight the Seattle F# user group is going to be presenting on, it's actually going to be both Dataflow as well as some of their OSS open source software project work. So if you're interested in those things, then please dial back in. I believe that's going to be 7 p.m. Pacific time. So hopefully we'll see some of you again. Thanks a lot.
Thank you, Ryan.